Alright, so now we're going to do discussion 6-3, chemical equilibrium. It's important to note that in your textbook, equilibrium is IB topics 7 and 17. So when we move on to the next unit, acids and bases, it's going to be unit 8. So there is no unit 7. Okay, so equilibrium. So many reactions do not go to completion. And some of those reactions that don't go to completion are reversible reactions. And what it means to be a reversible reaction is that reactants can combine to form products, and those products that are formed can combine to form reactants and go back in the opposite direction. So examples of reactions that do go to completion would be when two solutions are mixed and a solid precipitates out of the solution. Since the solid is no longer part of the solution and the ions are connected together, then they will do no more reacting in the solution. Another example is if a gas is formed and escapes from the solution. If the gas leaves the scene, then it won't be in the reaction vessel to continue reacting. And finally, one more example that you don't see in the slide here is burning wood in your fireplace. We know when we burn wood, it turns into ashes and smoke. But we can't combine ashes and smoke together to go back and form wood. Alright, so equilibrium is a state in a closed system where the concentrations of reactants and products remain constant. And they remain constant because the rates of the forward and reverse reactions are equal to each other. Now it's really important that you separate the words constant from equal, because although in equilibrium the concentrations are constant, they're not necessarily equal. It's the rates of the reactions which are equal. And dynamic equilibrium just refers to an equilibrium where the forward and reverse reactions continue to occur, but you don't see any changes in the concentrations of reactants and products. And a good analogy for that is running up an escalator that's moving down. In that situation, you're running up and the escalator is moving down, but there's no apparent change in your position relative to the ground. And that is because you are running up at the same exact pace that the escalator is moving down. Alright, so we can look at this graphically. Initially, the rate of the forward reaction starts fast and then decreases over time, and that is because reactant particles are being used up. Conversely, as reactant particles are used up, product particles are created, so the rate will steadily increase over time. Eventually, the two rates will equal and steady each other out, and that is when you are at equilibrium. We can also look at a plot of the amount of reactant and product over time. Initially, we have all reactants and no products. As time progresses, reactants are consumed and products are produced, and they'll continue to be consumed and produced until the concentrations steady out. That means that at equilibrium, you'll never have an amount of reactants equaling 0. You could have really, really tiny amounts of reactants remaining, but it'll never go to 0 because you're always going to need some reactants to form products. Alright, so some prior knowledge that's really important for this topic. 1, you have to be comfortable with the naming and formula writing of ionic compounds. You have to be familiar with their dissociation and their solubility. Also, it's really important that you're familiar with working with natural logarithms. Alright, so equilibrium expressions are equations that quantitatively show us how far a reaction will proceed. So if I have a generic reaction A plus B making C plus D with lowercase j, k, l, and m as their stoichiometric coefficients, then the equilibrium expression would look like this. K sub C is equal to the concentration of C raised to the L power times the concentration of D raised to the M power divided by the concentration of A raised to the J power times the concentration of B raised to the K power. Products raised to the power of their coefficients divided by reactants raised to the power of their coefficients. Now K sub C is what we use to denote the equilibrium constant. This K value is specifically for concentration. That's what that subscript C means. There are all sorts of other K expressions that we'll examine later. Now every reaction has its own unique K value, and it'll be constant for that particular reaction at a particular temperature. However, if temperature changes, the value of K sub C will change as well. So if we have numbers to plug into that equation, changing the temperature will change the value of those numbers, which will change the value of K. And temperature is the only thing that will change the value of K. So changes in pressure or concentration will have no effect. So take a moment to do this problem. It says write an equilibrium constant expression for the following balanced chemical equation. It gives you the combustion of methane. So take a moment, pause the video, and write the equilibrium constant expression for this reaction. Alright, so this time you see we have K sub P. Because we're talking about gases, this would be a K expression concerning pressure. And you see we have the concentration or pressure of carbon dioxide cubed times the concentration of gaseous water or steam raised to the fourth power divided by the concentration of propane times the concentration of oxygen raised to the fifth. Pretty easy, right? Now this is an example of a homogeneous equilibria because all the species involved in the K expression are in one phase. Now, it's important to note that we do not consider pure solids or liquids in equilibrium constant expressions because liquids and solids don't have concentration values. So we're only going to consider aqueous and gaseous species. So we saw in the previous example steam, gaseous water, but if that water were liquid, it would not appear in the K expression. So take a moment to write the K expression for this particular equilibrium. Alright, this time I called it KEQ, which is the general designation for equilibrium, because we can't call it K sub P or K sub C since we have gas and aqueous in the equilibrium expression, and that is an example of a heterogeneous equilibrium. Alright, so this is an example where we actually calculate the value for K. Problem says nitrogen dioxide decomposes at high temperatures according to this equation. So you have 2NO2 in a reversible reaction with 2 NOs and oxygen gas. Calculate the equilibrium constant if the equilibrium concentrations are as follows. And it gives you the values for concentration. So take a moment, pause the video, write the K expression, plug in the values, and solve for K. Alright, now in this case, it should say K sub P. I'm going to go ahead and change that right now, although it's a little bit awkward during the video. This way it'll be fixed when we teach it in class. Alright, so K sub P, there's our K expression. When you plug in the values, you should get 1.4 times 10 to the negative third. Alright, so whenever you're given the initial concentrations, you can use the equilibrium expression to determine how far the reaction will proceed and in which direction will be favored. So if K is much greater than 1, the reaction will favor the formation of products. That means that at equilibrium, you'll have a lot more products than you do reactants. And if K is much less than 1, the reaction will favor the formation of reactants. And it's really easy to look at this if we look at a K expression. If the value for K was going to be much greater than 1, then we would expect the numerator of this equation to be much greater than the denominator. And if the numerator is greater, that means that we have more products than we do reactants at equilibrium. And if K were going to be a very, very small value, that would mean that the denominator would need to be much bigger in comparison to the numerator. So that would mean that we have much more reactant at equilibrium. So we can see in this particular case, the value is less than 1, so the reactant side of the equation will be favored. Alright, so super secret information. I'm assuming it's super secret because a lot of this we're going to look at in Unit 8. So like I mentioned, KEQ is the general designation for an equilibrium constant. K sub C concerns concentration. K sub P concerns pressure. KSP is called the solubility product, which shows us how much of an ionic solid will dissolve in water. Ka and Kb are acid and base equilibrium constants, and Kw is the ion product concentration, the ion product of water, And again, these last three we'll look at a lot in Unit 8. Now, it does not matter what the subscript on K is. Equilibrium constant expressions are always denoted with a capital K. The subscript just tells us what type of K constant we're looking at. Alright, so predicting reaction direction. So in order to predict the direction a reaction will need to proceed in order to establish equilibrium, we use what's known as the reaction quotient. And the reaction quotient is denoted with a capital Q. So to determine reaction direction, we'll write the K expression, but instead of using K, we'll use the capital Q. Then you'll solve for Q. We'll compare our results to K. Now, if K is equal, or if Q is equal to K, then there'll be no shift. If your Q value equals the K value, then that means you're at equilibrium. If Q is greater than K, that means the reaction will need to shift left, forming more reactants. And if K is less than Q is less than K, it'll have to shift right. So basically, the concentrations given to us, if we're using Q, are concentrations that may or may not be at equilibrium. We're not sure. And so we're going to solve for Q to find out. So here's an example. It says 0.5 moles of SO2, 0.1 moles of O2, and 0.7 moles of SO3 are introduced simultaneously into a 1 liter vessel at 1000 Kelvin. For the equilibrium 2SO2 plus O2 making 2SO3, the value of K at 1000 Kelvin is 280. So the first thing we'll do is ask, is the mixture at equilibrium? So we'll solve for Q and compare to K. So when I write the Q expression and plug in the numbers, I get a Q value of 19.6. So no, we are not at equilibrium because 19.6 is not the same number as 280. So now the question becomes, if it's not at equilibrium, which direction will the reaction need to proceed? Well, 19.6 is a much lower number than 280. So to increase this number to get to K, then we have to increase the size of the numerator to make a larger number. That means that the reaction will have to shift toward the product side of the reaction. All right, calculating K using ICE problems. So ICE problems are used when the problem gives us data. It'll give us data on initial concentrations of reactants and products and equilibrium concentrations of reactants and products. And we can use that data and our chemical intuition to figure out the equilibrium concentrations for all of the reactants and products. And ICE is an acronym for initial, change, and equilibrium. So when we do ICE problems, the first thing we do is make a table. Along the top of the table, we'll list each of the reactants and products with their stoichiometric coefficients. We'll then make 3 rows, I, C, and E. We'll record any known concentrations, that is, concentrations that the problem gives us, or ones that we can infer using our chemical intuition. We'll then use stoichiometry to ascertain the C row, and plug in our equilibrium concentrations that we find by doing that into the K expression and solve for the unknown. So let's look at an example. It says hydrogen and iodine are in equilibrium with hydrogen iodide according to the following equation. Suppose that 1.5 moles of H2 and 1.2 moles of I2 are placed in a 1 liter container. At equilibrium, it was found that there were 0.4 moles of HI. Calculate the equilibrium concentrations of H2 and I2 and the equilibrium constant. All right, so here's our table. We have 2 reactants and 1 product. So I wrote 3 columns with each reactant over a different column, each reactant or product. And now I'm going to input the known concentrations. Well, the problem tells us that we're going to mix 1.5 moles of H2 and 1.2 moles of I2 into a 1 liter container. That's why I was able to change the unit to moles per liter, because we're in a 1 liter container. And it tells us that the equilibrium concentration of HI is 0.4. Now, one thing it does not tell us is the initial concentration of HI, but we should be able to work that out just using our chemical intuition. Because at the moment the reactants are mixed, initially the concentration of any product will be 0. I didn't mean to have that pop up, but that's okay. So now that we know that, we can calculate the change in HI. If we started at 0 and produced 0.4, then 0.4 moles of HI were produced. All right, now's where we use stoichiometry. I know that for every 2 moles of HI produced, I would use 1 mole of I2 and 1 mole of H2. So the concentration, so the change, in H2 and I2 is minus 0.2 moles. Now that I know that, I can calculate the equilibrium concentrations of H2 and I2, write the expression for K, plug in the values, and solve. And in this case, I get K is 0.12. All right, equilibrium and Gibbs free energy. So the value of K is related to the maximum value of entropy and the minimum value of Gibbs free energy. It can be expressed by the following equation. Delta G equals negative RT times the natural log of K, where delta G is Gibbs free energy, R is the universal thermodynamics constant, 8.314 joules per mole Kelvin, T is the temperature in Kelvin, and the natural log of K is the natural log of the K expression. So here's an example. It says calculate the equilibrium constant at 300 Kelvin for the oxidation of iron. It gives us an equation, and it gives us a value for delta H and delta S. So at this point, you need to know, since it's talking about an equilibrium constant expression, and it gives you values for delta H, delta S, that should tip you off that you need to use delta G equals negative RT times the natural log of K. So the first thing I'll do is plug into delta G equals delta H minus T delta S to find delta G. When I plug in the numbers, I find that delta G is negative 761.2 kilojoules per mole. And please remember, if the temperature is given in Celsius, you have to convert it to Kelvin, and you have to divide your delta S value by 1,000. So now that we have delta G, we also have R because it's a constant. We have the temperature in Kelvin because it's given to us, so now we can go ahead and solve for K. So the first thing I'll do is isolate the natural log of K, and then I'll take the inverse natural logarithm of both sides to get K equals E raised to the negative G divided by RT. Now, like I told you, if you are unfamiliar working with natural logarithms, you really should be, so I'd recommend, if you're not, watching a few YouTube videos or asking your math teacher and getting caught up on that, or asking me during a free time. All right, so when we plug into our equation, we get K is equal to 1.357. Okay, Le Chatelier's principle. So Le Chatelier's principle was something we covered in 10th grade, and it says that if a stress is applied to a system in equilibrium, the equilibrium will shift so as to minimize the effect of the change. In other words, Le Chatelier's principle says that if you do something to the equation, the reaction will work to reestablish equilibrium. And there's 4 things that can cause a shift. 1, adding more product or reactant, removing a product or reactant as it's formed, changing the pressure, or changing the temperature. And remember that changing the temperature will also change the value of the K expression, but it will not change, but these factors will not. All right, so changing a reactant or product. So here we have generic equation A plus B making C plus D. So what will happen if we add more A? Well, if we add more A or increase the concentration of A, we're increasing the number of reactant particles. That means there'll be more collisions on the reactant side, and the rate of the reaction will be pushed toward the product side. Now, I also like to think about this like a tube of toothpaste. If we have a full tube of toothpaste and we jam more toothpaste on the reactant side, that's going to cause toothpaste to be squeezed out onto the product side. So if I add more A, it'll shift toward products. If I add more D, the same thing will happen, only in reverse because we're adding more product, and it'll shift toward reactants. Now, if we remove C as it's formed, also think about this toothpaste example. If we remove C and we have the full tube of toothpaste over here, that would almost be like causing a vacuum effect where we would need to replace the C that's being lost. So as we remove a product as it's formed, the reaction will shift toward the formation of products. All right, so changing pressure. When I look at an equilibrium of gaseous reactants and products, if we change the pressure, we can cause the reaction to shift. And when we're looking at these systems, it's important to look at the number of moles of gas on each side, because pressure will always flow from high pressure to low pressure. That's actually how weather works. All right, so I see that I have 4 moles of gas on the left side and 2 moles of gas on the right side. We're assuming that all of these gases are in the same vessel, so the partial pressure of hydrogen and nitrogen is greater than the partial pressure of ammonia. So if I increase the pressure is going to flow from high to low, so it's going to flow from the side with more moles of gas to the side with fewer moles of gas, or toward the products. If I decrease the pressure, the exact opposite will happen, and it will shift toward reactants. It's important to note that if there are equal numbers of moles on both sides of the equation, then increasing or decreasing the pressure won't cause a change in that equilibrium. All right, so changing the temperature. So when we're looking at changes in temperature, we have to remember that in a reaction, heat will be either a product or a reactant. Now, if it's an endothermic reaction, that means heat would be a reactant, and if it's exothermic, that means heat is a product. It's also important to know that changing the temperature will change the value of K. So for an exothermic reaction, if we increase the temperature, we'll shift toward the reactants because we're adding a product. But not only will the equilibrium shift toward the reactants, but the value of K will shrink as well because it'll be pushing it in the direction of the reactants. If we cool the reaction, the exact opposite will happen, and the reaction will shift to the products, which would cause the value of K to increase. All right, so adding a catalyst. Now, catalysts only increase the rate of a reaction by lowering the activation energy. So adding a catalyst lowers the activation energy for the forward and reverse reactions equally. So adding a catalyst won't have an effect on the official position of equilibrium, but it will help the system get to equilibrium faster.
Alright, sorry about the jump there if there was one. I'm just inserting something into this video, a little change. Okay, so it's time to puzzle it out. I want you to stop and think about this for a moment. So the reaction we looked at before, the Haber process, where nitrogen and hydrogen combine to form ammonia. The question says, based on Le Chatelier's principle, it makes sense to cool the reaction and increase the pressure to maximize the products. However, the reaction is conducted at high pressures and temperatures. Why? So take a moment and pause the video and see if you can puzzle this out. Use what you know about equilibrium and kinetics, and I think you can come up with a decent answer. Okay, so it says it makes sense to cool the reaction and increase the pressure to maximize products. Now that makes sense. Because this is an exothermic process, if we cool the reaction, it will push toward the formation of more product. And because there are more moles of gas on the left side of the equation, when we increase the pressure, it'll also push the reaction toward the formation of product. Right? However, we're going to conduct this at high pressure and high temperature. So using high pressures, of course, will shift the equilibrium toward products, and that makes perfect sense to do then. But the reason we do this at higher temperature is because in order to react the nitrogen with the hydrogen, the bonds between the nitrogen atoms and the hydrogen atoms must first be broken. And if you recall from Unit 4, the bond between two nitrogen atoms is a triple bond. And so that is a very, very, very strong bond. You can actually look up its value in the data booklet. It takes a lot of energy to break that bond. So this reaction, the forward reaction, has a very, very high activation energy. And so we need to have this reaction conducted at a high temperature in order to make that forward reaction go in the first place. Okay.
To kinetics to equilibrium. So, a couple questions to ponder. A reaction with a very large K value. Comment on the speed of this reaction. What can you tell from K about the reaction rate? So I know that if I have a very large value for K, then products are favored over reactants. And if the rates of the forward and reverse reactions are equal at equilibrium, that must mean that the initial rate of the forward reaction was much, much greater than the initial rate of the reverse reaction. Right? So if the reaction rate of the forward reaction rate initial rate is a lot faster, we could tell that K would have a large value. And if the initial rate of K, or if the initial rate of the reverse reaction was very large, then we would know that we would have a lot of reactant and K would be very small. And again, if I add a catalyst to the reaction, it's not going to have any effect on the value of K. Only temperature affects the value of K, but the catalyst will help to get to K faster. Alright, so what can affect K? Only temperature. And how is this possible? By energetics. The available entropy and Gibbs free energy of reactants and particles can have an effect on the value of K. And an example of this is an equilibrium between a liquid and its vapor. So even when a substance is in the liquid state, some of the molecules will escape and become gaseous. Each liquid will have its own unique vapor pressure at a given temperature. And of course, Liquids that have weaker intermolecular forces will have higher vapor pressure. So let's examine the equilibrium between gaseous and liquid water. And that should be a double arrow there. All right, so we know that evaporating water is an endothermic process, right? So if we increase the temperature, because heat is a reactant, then we'll increase the vapor pressure and the amount of steam produced due to the shift toward the products. Now, if we want to look at increasing pressure on vapor pressure, well, if we look at this, having more steam represents a higher vapor pressure. And if we increase the pressure on this equilibrium, then nothing is going to happen because there's only gas on the right side of the equation. So the only thing that will change the vapor pressure is temperature. And now the effect of pressure on boiling point. Well, boiling, the definition, is a point at which the vapor pressure is equal to the atmospheric pressure. Decreasing atmospheric pressure means that you don't have to heat water up as much in order to make it boil. Right? So decreasing pressure will have that effect on the boiling point. The less pressure above, the less temperature, the less energy is required to make it boil.
All right, so that is all. As always, thank you for watching. If you have any questions, please bring them to class.